Well, it's 6 p.m. and this is the Randomizer. I'm Charles Schultz, hosting the show. I'm the founder of Schultz Laboratories and the Universe Science Center. Take a chance, go to our site, schultzlaboratories.com, universesciencecenter.com, and become a member. Sign up. See our ever-growing library of technical videos and informative material, and walk through our virtual galleries. We have a whole world of stuff in there. Put your Oculus on, or use your laptop or whatever. Explore our galleries, play with the exhibits, learn some stuff. It's a great deal of fun, and we hope that your support will help us add more galleries, add more content, and grow the whole thing. So this evening, we have a very special subject. You know, I love the randomizer. It creates so many interesting ideas, and tonight it has selected a name, Carl David Anderson. So what's important about Carl David Anderson? Well, he's a physicist. He was born in 1905, and he started his studies out in looking at the distribution of photoelectrons emitted by gases under the influence of X-rays. He was interested in X-rays. And you know, back in the 30s, X-rays were a big hot topic, and a lot of study was done. And so what happens in a near vacuum if you put some gas in there and you blast it with X-rays? Well, what would happen, the X-rays carry a lot of momentum. They are photons, which are momentum. And when they would strike the electrons of some gases, they would knock them free, and off these electrons would go. Now, there's an interesting thing about charges and magnetism. If you were to place a magnet in the path of charged particles, and you could see those particles somehow, you would see that a left-handed spin would come from one charge and a right-handed spin from the opposite charge. So he used something called a cloud chamber, a Wilson cloud chamber. And particles passing through the cloud chamber, or even a sheet of photographic film, would create a very characteristic spiral path if it's an electron. And what happens as an electron is it spins in a spiral, it's changing velocity, and it's giving off photons as it goes, and slowing down. So this little spiral would form always in the same direction around the magnet pole when it was an electron. Once in a while, he saw a spiral that was exactly the same, but it was backwards. Makes you think. It looked like an electron, but it had to have a positive charge instead of a negative charge. So the big thing back then was cosmic ray studies, and people were interested in the universe. And Dr. Anderson studied the universe and cosmic rays, and he did experiments with them as well. And one of the things he found was the cosmic rays would strike matter and give off these particles that spun backwards. And so the magnetic field was the way of detecting it. And what was this particle? When he did the analysis, he discovered that it actually was the opposite of an electron, an anti-electron. Now, to make this clear, all the particles that matter is made of have a specific spin, charge, magnetic field, and mass, certain properties that we know very clearly and very, very precisely. So what is this mystery particle that was being created? Well, they came up with a name for it. Instead of electron, which is sometimes called a negatron because of its negative charge, they called it a positron. So positrons are very interesting particles because they are made of the same stuff that regular matter is, but due to the fact that its charge is backwards and its spin is backwards, when they encounter a normal matter particle, it explodes. They annihilate each other. This was the discovery of antimatter, and it had never been seen before. Now, antimatter actually happens numerous different ways in nature. It was long suspected when this was discovered that possibly there were whole clusters of antimatter in the universe making star systems or galaxies. We know this is very unlikely right now, although some people think it's possible. But we do see antimatter produced in many different reactions. One of them is called the beta decay reaction. You see, there's two nuclear forces that hold matter together. And the strong force is what holds the particles and the protons and the neutrons together, makes the matter we have possible. The weak force is another type of binding force in nuclear matter. And the weak force has different ways to make things decay. It moderates certain types of nuclear decay. If you have a particle that, let's say you have a gamma ray, a very energetic gamma ray, and it strikes a proton. If there's enough energy in it, the proton will shatter and particles will come out of it. One of those particles is a neutron, one will be a positron, and one will be a neutrino particle, which we won't get into right now, but it's just like a ghost. It goes to anything. The positrons are emitted in this reaction called positive beta decay. Negative beta decay is where a gamma ray hits a neutron, turns into a proton, and an electron antineutrino. So why? Well, everything is bookkeeping. All of the numbers always have to add up to the same thing. And you've heard of the conservation law. Energy isn't created or destroyed. Matter isn't created or destroyed. Well, we learned a long time ago, due to this research and Einstein's work, that matter and energy are interchangeable. But matter can be changed into energy, energy can be changed into matter, but in the end, you always have the same sum total amount of energy. And you have the same sum total of charge and the same sum total of spin. So all of these things always have to add up to the same number. And that conservation law is fundamental to our universe. So when beta decay occurs, sometimes you get an electron, sometimes you get a positron. And an electron and a positron, when they combine, vanish in a burst of gamma radiation. So that's an antimatter reaction. Now, we can actually make antiprotons also, and this has been done. They were accelerated up to high speed, protons themselves, in a linear accelerator. And when they got up to high speed, very close to the speed of light, a target was placed in their path made of tungsten, a very heavy element. And the protons striking the tungsten target would often create nuclear debris, and antiprotons would spray out of the back. They were moving so rapidly, they didn't have time to react with the other matter and get annihilated. Now, you place a charged plate in their path that's negatively charged, and it slows them down like a shock absorber. And you put a magnet there, and it curves their path, and you can catch them and decelerate them and trap them in a device known as a penning trap. So scientists have produced positrons, and they've trapped them in a penning trap, and they've produced antiprotons and trapped them in a penning trap. And by putting these two different antimatter particles together, have created anti-hydrogen. This is the first time that stable antimatter had ever been made. And there were some very interesting questions about it. Would it act the same as normal matter? The chemistry in it should act exactly the same. How about if we drop it? Will it fall downhill? Yes, it does. It falls normally under the influence of gravity. So matter and antimatter are two faces of the same coin. Every time you take energy and make matter, you will get an equal quantity of antimatter. Because again, all the bookkeeping has to add up to zero. It all has to add up to the same number you started with. So you don't get anything for free. You put a lot of effort in. You'll transform something, but you won't get anything for free. And that's basically one of the fundamental principles of conservation in the universe. So now what's so interesting about this? Well, this led us to understand, and let me go back a second here. He did win the Nobel Prize in 1936 for his 1932 discovery of the positron, of antimatter. In 1936, he went on to discover another particle called the muon, which is essentially just like an electron, but 207 times heavier, and it can break down. It isn't very stable. Muons can actually be put in orbit around an atom and knock an electron free, and the muon will orbit very close to the nucleus, close enough that it can actually draw atoms together and catalyze hydrogen fusion. And there was a Soviet scientist, Andrei Sakharov, who was the dissident sent to Siberia. He figured out a lot of things about muons, including muon catalyzed fusion. And this is actually a leading contender for making nuclear fusion work in fairly pedestrian environments. The problem is making the muons, but it does work. So let's get to the properties of antimatter and the weak nuclear force, because there's something very, very interesting that emerged from all of this. Life on Earth has a very specific biochemistry. We are made of left-handed proteins and amino acids, and right-handed sugars are used in our metabolism. Years ago, they made left-handed sugar, which chemically is the mirror image of the molecule. It's the same matter, but it's like a right or left-handed version of the molecule. Left-handed sugar tastes just as sweet, but it does not get digested, and so it doesn't add anything in terms of fat. So it was touted as a means of having sweeteners that wouldn't affect your diet and wouldn't put any weight on you. And it does work, but some people have a bit of a reaction to it. But why are our proteins and enzymes and amino acids left-handed only? We may have an answer to that. And it has to do with that weak nuclear force that causes positrons to sometimes be emitted in nuclear breakdown. Our universe is examined through a number of lenses in terms of physics. And one of them is called the CPT model. And that's charge, parity, and time symmetry. So the idea is matter and antimatter have charge symmetry, but they're mirror images of each other. And they have spin symmetry, but they're mirror images of each other. And time, many processes in time will run forward or backward equally likely. And so we can create this thought experiment universe by looking at everything in a mirror. So CPT symmetry is that model, and it's a test case. Think of it as that. It allows us to test some assumptions about physics, do the math, and see how it works out. And we can often predict things and then discover them later on. And there was a fellow by the name of Hideki Yukawa who predicted the existence of the pi meson by using these models and some mathematics, and he was absolutely correct. The particle was determined to exist later on. But that's neither here nor there. What is most interesting is when you produce an electron through beta decay from the weak nuclear force, the force is slightly asymmetrical. It isn't an exact mirror for matter and antimatter. And it turns out that the electrons created in this way often have a left-handed spin. They're left-handed spin polarized. Why? Nobody knows. But it seems to be an underlying structure of the universe. Our whole universe is slightly left-handed. Well, what's important about this is the electrons produced will destroy a certain form of amino acids. In other words, if radiation present early at the beginning of life produced these left-handed electrons, they would ionize and destroy certain organic molecules only, one-handed and not the other. And this could have tipped the biochemistry of the Earth to left-handed amino acids. It isn't known for certain, but the experiments do show that it happens. So our universe actually has a handedness, a spin-handedness. So it's kind of like if you spun a whole bunch of gyroscopes and 3/4 of them were spinning one way and 1/4 the other way. Well, you'd notice that something very odd was happening because they should all spin the same way. So our universe has an underlying handedness. And the discovery by Carl David Anderson earned him the Nobel Prize in 1936 for the discovery of antimatter, the positron. And the studies of X-rays and then positrons and their emission led to a potential answer to the handedness of our universe. It's not perfectly symmetrical, and possibly the left-handed nature of the life on Earth. A fascinating series of connections from basically a nuclear physicist, a Nobel Prize winner from 1936. So I hope this is an interesting story, and it led us along a long path, but it shows us some very fascinating things. In the future, antimatter could prove to be one of the best power storage devices we will ever have, and has certainly been proposed as a means of fueling spacecraft that could be incredibly small compared to what we have today. If we were to launch a mission to the moon using an antimatter powered spacecraft, it would be about the size of a Volkswagen bus, not needing something the size of the Saturn V. So this is just kind of an indicator of the incredible power of antimatter. Well, that being said, I'm going to encourage people to go to schultzlaboratories.com or universesciencecenter.com and sign up for our weekly courses Monday evenings, 9 p.m. Eastern Standard Time. We are going through our Meta World classes, and we'll be doing class 3 Monday. That's the 14th. Also, become a member of the Universe Science Center and help support our galleries, our materials, and our growth. Go in and explore, get your Oculus or your Vive, walk around in there and have a great time, and give us suggestions, what material you'd like to see, what classes you want your kids to learn, and we'll build them. We'll put them in there. That's what it's all about, bringing equitable, factual education to people through a virtual environment. So now, if anybody has any questions, the floor is open, and otherwise I'm going to continue to ramble about technical subjects. And I don't see any questions emerging. Well, all right. So it's funny, a lot of study of X-rays and cosmic rays have actually led to a number of really interesting things, and this is just one of them. And I think that, we're always looking at the universe to try and discover things, but it's only when we get to the actual extremes of energy and mass and scale that we start finding the interesting stuff. And on the subject of the universe being left-handed, I found an interesting statement. In Judges 2016, among all these soldiers, there were 700 select troops who were left-handed, each of whom could sling a stone at a hair and not miss. So maybe there could be some advantages to left-handedness sometimes. Well, with the lack of further questions or suggestions, I'm going to call this one to a close, and I appreciate everybody's watching and support. And I hope to have more fascinating material. We'll have another randomizer tomorrow at 6 p.m. Eastern Standard Time with another randomly selected subject. So everybody have a good life, take care of yourselves, and make the world a better place. And thank you.